Hey, what's up, Algebra 2? It's Ryan. Today we're going to be working on domain, function operations, and composition. So, domain is going to be important when we're talking about pretty much any function and where it's defined. So we're going to be learning about that today, some common domain restrictions. And we'll also talk about composition. And some ideas we learned today in composition are also going to be brought up when you eventually take calculus and you learn about the chain rule. So there's some ideas that are pretty reminiscent between those two. So yeah, today will be a good lecture. Okay, so let's first talk about domain. So domain is essentially the interval of x values where we have a y value. Okay? And so when I say where we have a y value, that essentially means where the function is defined. Okay? So we wanna um we wanna find y values that are real in that function. X values that elicit y values that are real. So we to sort of define the domain or to find the domain, we want to think of values of x that would make the y value not real, okay, or imaginary or undefined. So one example of this would be the function 1 over x, okay? And pretty much any any function where we have an x in the denominator. Because when we have an x in the denominator, we can set x to some sort of value where the denominator can be equal to 0. And obviously when we divide by 0, we can't do that. It gives us an undefined value. So for example, if we were to graph, let's try graphing 1 over x. So if you plug it into Desmos, you'll see that you get something that looks like this, okay? Right? Something like that, okay? So this is called a rational function, but essentially our function 1 over x, when we approach this y-axis from the right side, we get real close to the y-axis, but we never touch it. And that's the definition of an asymptote. So we have an asymptote along the y-axis. Okay? Similarly, when we approach the y-axis from the left side along here, we get really close to the y-axis, but we never touch it. So along this y-axis, we don't have any x values that are defined. Our y value is not defined along that y-axis. Okay? So our domain is essentially going to be the range, or not the range, but the interval of x values, where we do have a y value that's defined. And so the way I like to think about domains is as we move across the x-axis, we pick out certain values of x and we see, do we have a y value there? So for example, right here, do we have a y value? Yep, right there. Here, do we have a y value? Yep, right there. Do we have a y value here? Yep, right there. And then we get to x equals 0 along this axis, we don't have a y value. Do we have a y value here? Yep, right there. Do we have a y value here? Yep, here, yes. So it's basically anything that's less than 0 or greater than 0, but just not 0. Okay? So when we talk about where our function 1 over x is defined, or what's the domain of it, we're just going to say it can't be 0. So we either say, right, we said it has to be, let's do like a red. We know it's either defined here, or anything less than 0 or greater than 0. So we'd say x is less than 0 or x is greater than 0. Another way we'd write this in interval notation, which I tend to like interval notation. But we'd start from the left, and it goes all the way infinitely in this left direction. So it goes to negative infinity. And we use this parentheses to signify that it's not inclusive. And we use a parentheses when we're talking about infinity, negative infinity or positive infinity, because we can't ever reach infinity. So we have parentheses negative infinity, and it goes all the way to 0. But 0 is not included. So we do another parentheses. Then we use a union, and now we need to talk about all this part where x is greater than 0. And we start at 0 again, but 0 is not included, so we use a parentheses, and we go all the way until positive infinity, and another parentheses. So that's one case. Now let's talk about even roots. So even roots, an example of that would be, let's just do the square root of x. And this is actually going to be one of the examples we do below. So the square root of x essentially has this invisible index 2, right? If we don't see an index, we assume it's 2. And so we have an even root since this number is even. Okay? So let's start, I'll create the graph after, but let's start thinking of values where x is defined. So can we take the square root of, let's say, 4? Yeah, the square root of 4 is going to be 2. Can we take the square root of 7? Yes, we can take the square root of 7. It's going to be a fraction, but we can still take the square root of 7. Can we take the square root of 289? Yes. Can we take the square root of 1,000,000? Yes. So we know x is going to be defined for all positive numbers. Let's now go in the other direction. Let's first talk about 0. Can we take the square root of 0? And the answer to that is going to be yes. We can take the square root of 0 because the square root of 0 is just 0. Because 0 times 0 is 0. Okay, so it's defined for 0. Now, let's go into the negatives. Let's talk about -1. Can we take the square root of -1? So if you think back to what we've talked about prior in this course, we can't. Because the square root of -1 is going to be I, which is imaginary. So it's not real. This is not real. And since it's not real, it's not defined. The square root of x is not going to be defined for any, or it's going to be imaginary for any values of -x. Okay, for any negative values of x, my bad. So yeah, that goes for we can't take the square root of -9 or -121, right? Okay, so when we eventually graph this, and I'm just going to create this, not really dive too deep into this, but if you go on Desmos and try to graph it, it's going to look something like that, okay? Where we do have, where y is defined at x equals 0. So essentially, if we do what we did before, when we talked about, going along the x-axis and seeing do we have values of y where it's defined. Right here, we don't have a y value. We don't have a y value here. We don't have a y value here. We don't have a y value for any values of x that are negative. Do we have a y value at 0? Yes, we do. Do we have a y value here? Yep. Yep. And forever in the positive direction. So we'd say, and real quick, I'm going to relate this to this equation we have down here. So before, we've talked about that the square root of x is actually going to be equal to x to the 1/2 power. So we see x to the 1/2 power here. We can say that's equal to the square root of the x. And now we're going to say, where is x not defined? X cannot be, how should I write this? It cannot be any negative values. So what I'm going to say is I'm going to write this as x must be greater than or equal to 0. Or how I'd write this in interval notation is that x must be equal to 0. That's why I use the brackets, or greater. So it must be like that. And then we use the parentheses. Okay? Great. Now, so essentially, x is going to be defined for any value here on out. Okay? Great. Now let's just go through some of these examples of restricted domains and try to find values of x, or try to find the domains, okay? And then we'll talk about some of these cases where our domain is all real numbers, okay? So first, in this case, we have a rational function. We have x in the denominator. We know that our denominator cannot equal 0. So what value of x gives us a denominator that's equal to 0? That's going to be -5. So we're going to say x can be anything but -5. And I'm just going to start writing this in interval notation because I like that best. We know that we go from -infinity all the way up until -5. -5 is not included. Then we do a union and we go from -5 non-inclusive to positive infinity. Now in this case, we have a square root, an even root. So we're looking for values that make this radicand, or basically our what's under the radical, non-negative. Okay, so we want x minus 3 to be greater than or equal to 0. So we just say, if we just move this over, x must be greater than or equal to 3. Okay, if we just add 3 to both sides. So this is going to give us 3 all the way to positive infinity. And 3 is included, and that's why I use the brackets. Okay, in this case, same thing. We want a non-negative sort of, why am I blanking on the term? We want x minus 2 to be greater than or equal to 0. Sorry. So x must be greater than or equal to 2. And this is going to give us 2 to positive infinity with 2 included. Now in this case, we have sort of a combination of both, right? We know that x, so first of all, this is a rational function. So we know that our denominator cannot equal 0. Let's just write this out here. We know that the square root of x minus 1 cannot equal 0. But we also know that the square root of x minus 1, we know that x minus 1, what's under the radical, must be greater than or equal to 0. And there's sort of an and in between these. So we have to satisfy both of these sort of statements. So what value of x makes the square root of x minus 1 equal to 0? Well, that would be 1, because 1 minus 1 is 0. The square root of 0 is 0. So x cannot equal 1. or sorry, why did I say 0? X cannot equal 1. Now in this case, where we have x minus 1 must be greater than 0, we can rewrite this to say x must be greater than or equal to 1. Okay, so again, there's an and in between this. We know that it must satisfy both. So essentially, if we were to draw this on a number line, and we had 1 right here, we have one thing saying it must be greater than 1 with 1 included. That's this statement. We have a second statement saying it can be anything but 1. And so where do these two overlap? Well, they overlap. I'm feeling like using a lot of color today. It's basically anything that's greater. How should I do this? Something like that. It's basically anything that's greater than 1 without 1 being included, right? Because 1 can't be included here. And right, we want to see where both of these functions overlap because we're using and. So we're going to say x must be greater than 1. Okay? And because essentially this statement says x cannot equal 1, that means we have to take out this. Okay? This and or equal to sign. So x must be greater than 1. This means we have 1 non-inclusive all the way to infinity. Okay? Great. Now let's quickly talk about some functions where their domains are all real numbers. These are essentially going to be, so all real numbers means it can be 2, 1 million, 0, -5, whatever. And all polynomials, so polynomials of the first degree would be linear, like 2x minus 1. That's going to be a polynomial. Polynomials of the third degree, x cubed plus 2x minus 5. Everything like that is going to be going to have a domain of all real numbers because we can cube anything we want. We can multiply anything we want by 2, okay? We also have even roots, okay? Because say we were to take odd roots. Say we were to take the third root of 8. That gives us 2. 2 is going to be a real number, so that checks out. If we were to take the square root or the cube root of 0, that's going to be 0 because 0 times 0 times 0 is 0. So that checks out. That's a real number. Can we take the square root cube root, of -8? Yes, that's going to be -2 because -2 times -2 is 4 times -2 is -8. So that's going to be a real number. So anything with the odd root here, you see this x, or the fifth root of x, that's going to be have a domain of all real numbers. This x to the 1/3, we talked about this earlier, that's going to be equal to the cube root of x. That's also going to have a domain of all real numbers. So those are some examples. Yeah, that pretty much goes through everything. In this one case where we have f of x is equal to 3, we need to think about where f of x, or let's try to graph this. F of x is equal to 3 means y is equal to 3. That means no matter what our x value is, y is 3. So that it's just going to be a horizontal line where this is 3. Okay? And so that means x is defined for all values. It doesn't matter what x is, y is always going to be 3. Okay, so that checks out too. Okay, so let's move on. I know we spent a while on that. Let's move on to some operations of functions. Okay? So first, let's talk about, we have two functions, f of x and g of x, where f of x is 2x squared plus 3, and g of x is 4x cubed plus 1. We have a couple of functions. We have a sum, so that means adding. So when we say f plus g of x, that's going to be equal to f of x plus g of x. So in this case, f of x is 2x cubed, 2x squared. I'm going to write this off to the side. 2x squared plus 3. And we need to add g of x. So g of x is going to be 4x cubed plus 1. And once we combine this, we need to combine like terms. That's going to give us, actually, I'm going to write this here. That's going to give us 4x cubed plus 2x squared plus, we do 3 plus 1, that's going to be 4. Boom. Now, when we talk about difference, when we say f minus g of x, that's equal to f of x minus g of x. So that would be 2x cubed plus 3 minus, and I'm going to put this in parentheses because remember, we need to subtract the entire g of x. So we need to distribute that negative sign. And so we're going to say that's equal to negative 4x cubed. So I'm just distributing that negative plus 2x squared. And then we have 3 minus 1. So that's going to be 2. Boom. Now let's talk about product. F times g of x, f times g of x is equal to f of x times g of x. That means we just need to multiply this. So we're going to say 2x squared plus 3 times 4x cubed plus 1. So remember, we need to FOIL. So we need to multiply 2x squared and 4x cubed. That gives us 8, and we just add the exponents of that. So we get 8x to the 5th. In this case, we have 3 times 4x cubed. That's going to be 12x cubed. In this case, we have, I know they kind of overlapped. We have 2x squared times 1. So we're going to say plus 2x squared. And then finally, we have 3 times 1, which is just 3. So we're going to get something like that. Jeez. Okay. Great. Now let's talk about quotient. Quotient's going to be like that, except dividing, of course. So f over g of x is equal to f of x over g of x, assuming, or as long as g of x does not equal 0, right? Because g of x is on the denominator and we can't divide by 0. So we're going to say, ooh. Yeah, okay. Great. Okay. So actually, if we just think right now of the domains of all of these functions, all of these are polynomial functions, right? Just like any polynomial here where we have x cubed plus whatever, all of these, since they're polynomial functions, are going to have domains of all real numbers, okay? Now, since we're doing quotients, let's, once we solve this, think about some values of x that would not be, or we would not have our function be defined, okay? I'll explain that more in a second. Okay, so anyways, we have to write f of x over g of x. So that's just going to be 2x squared plus 3 over 4x cubed plus 1. Okay, And normally we'd try to simplify it. In this case, I don't believe we can simplify, so we just write it like that. Okay, and if we just think about the domain, so right, as we said before, all of these are going to be all real numbers. By the way, that's how you signify all real numbers, just by that symbol. It sort of looks like an R with an extra line. At least that's how I write it. Or you can just say all real numbers. But in this case, we can't have g of x equal to 0, so we can't have our denominator equal to 0. So 4x cubed plus 1 cannot equal 0. That means 4x cubed cannot equal negative 1, or x cubed cannot equal negative 1/4, which means x cannot equal the square root or the cube root of negative 1/4, which is some value. I don't know. It's gonna be, yeah, it is gonna be something like the negative 1 over the cube root of 4. Okay. So anyways, yeah, that's where x cannot, it is not defined. So any other value of x. Okay. So you can, I'd say, try this practice problem where we have f of x is 8x and g of x is 2x to the 5/6 power, and try using finding the product of the two as well as the quotient. So now let's talk about composition of functions. And so essentially what this is doing is we're taking functions and putting them inside of another function, okay? So let's first talk about this. When I say f of x, f is a function of x, okay? So that means, like, if I say this is equal, geez, I don't know why it's doing that. If I say it's equal to x cubed plus 5x squared, right? It's a function of x, okay? Right, so we plug in x values and we try to find values of f of x or y, okay? When we're doing compositions, we're instead making f of x into a function of another function, g of x, okay? So essentially what this is saying, when we have g of x, or essentially what we're doing is, instead of making f of x a function of x, we're making it a function of g of x. So anytime we see an x in f of x, we're plugging in g of x. So we'd say g of x cubed, whatever g of x is, plus 5 times g of x squared, okay, if that makes sense. And that's sort of what we're doing with compositions, okay? And so the way we denote that is with this sort of hollow circle in between f and g, or you can write it like this, whichever you prefer. In this, by writing it this way, you can see more that f is a function of g of x, okay? And the way you read this is f of g of x, okay? And they both have to be functions of x, and essentially you just sub in g of x for x in the f of x function, okay? So let's try to implement this and practice doing it. Okay, so we're asked to find g of f of x, okay? So that means anytime we see an x in the g of x function, we need to plug in f of x. So in this case, g of f of x is going to be equal to 4 minus, and then we have an x here, so we need to plug in f of x, 4 minus x plus 2 squared. And that's, if we do all this out, remember we need to distribute that that negative eventually this is going to be, and you can, or no, that's my bad. You can do all of the math for this out when you FOIL this out, but you're going to get something like that, right? And this is just going to be equal to negative x squared minus 4x, right? Because these two cancel out. Okay, and so that's g of f of x. Now, f of g of x is going to be the other way. So anytime we see an x in the f of x function, we plug in g of x. So f of g of x is going to be, right, we see an x here, we plug in g of x, we have 4 minus x squared plus 2. We simplify this, combine like terms, we have negative x squared plus 6. Okay? Now, let's try this out here. Okay, so you can try a by yourself. I'm going to do b instead. So we have g of f of x. So, right, this is the same thing as saying g of f of x, like that. So anytime we see an x in the g of x function, we want to plug in f of x. So that means this is going to be equal to 2 times, when we see an x, so we plug in x squared minus 6 minus 1. And this is going to be equal to 2x squared minus 12 minus 1. So that's equal to 2x squared minus 13. And I know I'm going fast with some of this simplification or simplifying. If you have, if I'm going too fast, just slow it down, pause, digest it, try it out by yourself. And yeah, if you do have questions, just reach out. So let's try, I should have done A. It's fine. I'll say this. Well, in this example, or actually, you know what? Let's just do A. F of g of x, that's going to be equal to f of g of x. First, try it out by yourself. I'll give you time to pause. So yeah, hopefully you've gotten an answer by now. Let's try doing this ourselves together. We see x in this x squared right here in this first term, so we want to plug in g of x. So that means we're going to have 2x minus 1 squared minus 6. And this is just going to be equal to, and I'm going to write this off to the side. I know this is kind of bad, but that's going to be equal to 4x squared. That's going to be minus 4x plus 1 minus 6. And that's going to be equal to 4x squared minus 4x minus 5. Okay? Great. Now, how you find f of g of 2 is you just plug in 2 into all of the x's. So when we plug in 2, that means 4 times 2 squared minus 4 times 2 minus 5. So this is 2 squared is equal to 4. So that's going to be 4 times 4 minus 4 times 2, which is just 8. I'm just going to write 8 there. Minus 5. 4 times 4 is 16. 16 minus 8 is 8. 8 minus 5 is 3. So that's our answer. Let's do D, just to get some extra practice. So this means we're going to have g of g of x. So that's equal to g of g of x. It might seem weird at first, but we're just doing the same thing. So we write out g, we have 2 times x. So since we have x, we need to plug in g of x for that x. So that means we have 2 times 2x minus 1. And then we're going to subtract 1 because that's part of our original outside g of x. So we just evaluate this to be 4x minus 2 minus 1. And so that's equal to 4x minus 3. okay? Now I want you to try it for these next sets of problems, all these different configurations. Remember that when we do have a value instead of x, just lean on what you did before, and B for D and A for C, and just plug in those values of x. So yeah, great. Okay, so let's now work on evaluating a composite function using tables. Okay, so in this case, we have a bunch of different functions. We have m of x, h of x, k of x, and v of x, right? They're all functions of x, and we're asked to compute some values. So in this case, we're asked to compute h of m of 5. So first, what we want to do is we want to find what's m of 5. So what's the function m of x equal to when x equals 5? So we go to this table, and we find what's m of 5. So what's m of x at x equals 5? That's going to be right here. And we see that m of x is equal to -1. So we need to find what's h of -1. And so we go to the h of x table. We find what's h of x equal to when x equals -1. That's going to be 4. 4. So we know this is now equal to 4. And boom, we have our answer. Now, let's try number C. So what's m of h of 2? So we need to first find what's h of 2. So right, actually, maybe this is more helpful to write it like that. What's h of 2 equal to? Well, h of x when x equals 2, that's going to be this value. So h of 2 is equal to 1. So we need to find what's m of 1. So m when x equals 1 is going to be 4. So this is actually equal to 4. Boom. Okay. Now let's I think hopefully you get the idea. It's just finding other values, plugging them in. So yeah, try those other 3. Okay. So now let's try to use graphs to help us with this. And by the way, I have some friends in calc doing calc right now, and when I took calc, it was the same. But there's something called the chain rule in calculus, and it's a big part of calculus. It's essentially eventually you'll get to super complex functions where, like, remember where in the very beginning we talked about this. F of x equals 2 over the square root of x minus 1. We have a bunch of little functions inside of bigger functions. We have a rational function since it's 2 over something. We have a radical, okay, so like a square root here, so that's another function. Then we have x minus 1, which is a linear function. And so essentially, chain rule helps us deal with that once you get to calculus and you take derivatives and stuff like that. Anyways, you have a bunch of little functions inside of bigger functions, and sometimes there'll be some tables, and you'll see tables like this where you need to find certain things and plug them into others. And yeah, so it's helpful to sort of learn how to think like this. So let's try using graphs to help us with this. For A, we have f of 0, or g of f of 0. So we first need to find what's f of 0. This function here is f of x. So what's f of x equal to when x equals 0? That's going to be 2. So what's g of 2? Now we go here, we find what's g of x equal to when x equals 2. So that's going to be along here. We find g of x is equal to 4. So A is going to be 4. In this case, this is read out loud as g of f of 5. So what's f of 5? What's f of x when x equals 5? It's going to be along this line. That's going to be 6. So now we need to find what's g of 6. Well, g of 6 is going to be the value of g of x when x equals 6, which is going to be 2. So this is equal to 2. Let's try one more. Let's try f. What's f of g of 8? Well, g of 8 is going to be the value of g of x when x equals 8, which is 5. So what's f of 5? We actually found it before. F of 5 is equal to 6. So this is going to be 6. Boom. Okay, and I think that's it for today. If you have any questions on some of the topics that we covered in this video, or any other problems relating to this that you want some help with, please reach out to your teacher, talk with your peers. Your peers are in the same class. They're learning the same material. They have the same experience as you. So reach out to them. They may be helpful. Also use the tutoring center as a resource. Maybe even reach out to some upperclassmen. Feel free to reach out to me, of course, anytime. I'm open. And yeah, use the internet as a resource too. There's loads of good information on this, on these sorts of topics there. Okay? Thank you. Have a good day.